Hello, I'm John Massick. I'm Senior Vice President of Bearing Service Incorporated, and I'm here today to talk to you about bearing failure analysis. If we look at bearings and how long they should last, uh, bearings have the ability to last many years, but in most cases, they just don't last that long for a variety of reasons. And what we're going to do today is we're going to kind of explore all the different reasons that bearings might fail prematurely. So let's go ahead and get started. So, wow, we started with kind of the mother load of bearing failures here. We are doing a bearing autopsy, and we see that the balls themselves are almost gone or misshapen. They're almost egg-shaped. We've got a retainer here that is in pieces. We've got other parts of this bearing that are broken. And even if we look at the bearing, this looks to be the inner race of a bearing. We can kind of see some areas where there might have been balls kind of at the spacing here that literally almost melted. So this is what I'm going to call a catastrophic bearing failure. And although this happens, this is not a typical bearing failure, but it's probably a great example of maybe the worst type of bearing failure that you could possibly see. And when bearings fail this way, they almost always fail because of heat. And when bearings fail because of heat, usually the number one cause of that is related to lubrication. The lubrication goes away, you get metal to metal contact, and the bearing steel starts getting so hot that literally it can start melting, or start the balls or rollers could actually start welding themselves to the raceways, which will cause the cage to rip apart and the whole bearing to seize, and bad things happen. Not only to the bearing, but sometimes to the shaft. It can break the shaft. It can ruin the customer's housing. So catastrophic bearing failures are really bad and cause a lot of equipment damage. So we really want to avoid those at all possible cost. But you'll see these once in a while, but not that often. So let's talk about bearing failures in general. So in terms of reliability of bearings, I have customers that say, John, you sold me a bad bearing. Well, it's almost impossible. Bearing companies during the manufacturing process check those bearing tolerances and noise and their ability to spin without vibration dozens of times during the manufacturing process. So the reliability of a bearing coming out of a bearing manufacturing plant is extremely high. Usually, if you see a bearing failure in the field, it's going to be caused from things like abuse. And by abuse, we're talking about the bearing not properly installed. Misuse would be bearing is the wrong application for a bearing. Maybe it needs to have some type of seal and it doesn't have that, and because of that, contamination occurs. Or misapplying the bearing. Talking about an application that has radial load and putting a bearing in there that can only accept axial load, for instance, would be a misapplication of the bearing. So important that we match the bearing to the application, and it's not only the right size, but that it really fits what you need that bearing to do. And so we're going to be talking about a variety of different types of failures today, and we got pictures, and I'll try to do my best to explain each one of them, and more importantly, how you or your customer can prevent these from happening going forward. So, in terms of failures in general, when someone says a bearing failed, it could be something as simple as the bearing is running hot, the bearing is noisy, but it doesn't actually stop turning. And depending on the type of end user you have, there's a lot of companies that might run a bearing until it fails. So called run to failure. And that's usually not a good idea, because when bearings run to failure and they fail, a lot of times they'll fail catastrophically and they'll take out other components of the equipment. So you usually don't want to do that. But other things related to failure is if the bearing seizes up or sees so much torque that it's no longer able to rotate properly. if the bearing is no longer able to hold its position. So let's say that the bearing is seeing a lot of axial load, and because of that, the inner race of that bearing is shifting over in relation to the outer race, and it's beyond the capacity of that bearing to handle that, then that's going to cause heat and failure. It's going to cause, they mentioned here, things like run out or wobble that could happen in bearings. And we'll be covering that, I think, in another class. I already mentioned about excessive noise or vibration. That's something that's actually can be measurable. And then temperature, which is another failure mode that is clearly measurable, and maybe one of the easiest ways to monitor bearings in terms of whether they're performing properly and whether they're going to fail prematurely. If the bearings are running at a constant temperature all the time, oftentimes in equipment, you can put your hand on that equipment. If you can put your hand on it, that means it's probably running below 120 degrees. And therefore, for most applications, that means that the bearing is probably operating properly. Why do you want to avoid bearing failures? Well, it's kind of a silly question, but sometimes bearing failures can impact safety concerns. If something breaks on a piece of equipment, and let's say it's an elevator motor, you don't want a failure on an elevator motor when people are in it. More commonly, it's dealing with downtime. In a typical manufacturing plant, a particular machine can have downtime costs that could be, in thousands of dollars an hour. In some cases, it's thousands of dollars a minute in terms of what a failure would be, and we want to avoid those at any cost. So, lost production. In an automobile manufacturing plant, for instance, when you're moving cars that cost $40,000 or $50,000 a piece, and your assembly line goes down because your bearing failed and you're down for an hour, that could be millions of dollars in lost production. Obviously, missed shipments to customers. If we're in a food plant, a lot of times the food's got to be, it has a shelf life. That's a problem if your bearings fail prematurely. And usually when they fail, it's extra expense to try to go ahead and change them out. So making sure that we understand bearing failures, why they happened, and how to prevent them in the future is really critical. We'll start looking at some pictures here of different types of bearing failures. And the first one here is showing poor lubrication or overload. And we're seeing this glazing of the raceway, and you see some sporadic little spots. And what that indicates is the high points of that steel, you're getting metal-to-metal contact here between the, in this case, it would be a cylindrical roller and this raceway here. And in that particular case, when you lack lubrication in between there, you're going to get this smearing of the steel, and you get that metal-to-metal contact, and eventually it's going to start out with a little small pockmark on the steel surface, and eventually, as it's shown here, that'll get bigger and bigger and bigger until you end up with what I call bearing chuck holes or spalling. What's this caused by? Could be everything from making sure I have a lubricant with enough viscosity to keep those surfaces separate from one another. Maybe I'm not lubricating that bearing often enough, or I lubricate it too much. Making sure that the bearing is properly sealed. This cylindrical roller bearing, for instance, does not have its own seals. They're not available. So you have to have auxiliary oil seals to be able to protect that bearing. Maybe the seals die. The seals have a life that's only about 10% of the life of a bearing. So sealing systems can fail prematurely, and then that'll cause bearing failure. And then if the bearing has too much load on it, for the size of the bearing, that can also be a problem, where overloading that bearing can start the deterioration process of the surface. Here's another one. Again, poor lubrication, overload. We've got some spots here. This is kind of the center line here of the roller would be going along the surface, and I'm having material high points of the steel being peeled off, and then again, that's a good indication that the lubricant viscosity is too thin, and I'm starting to get metal fatigue or metal damage between the surfaces. The high points of the metal will be pulled away. So here we're seeing peeling of the surface where you have the high points of metal being pulled away by the rollers as they're rolling over the raceway, and a lot of times that's caused from improper viscosity of the oil inside the grease. And so making sure we've got the right thickness of grease is critical. Some of the other conditions they showed here are the same ones on the previous slide. But over time, a small spot like this will create a much bigger and bigger hole in that bearing, that spalling I referred to, which is really severe bearing damage and will show up as noise, and potentially, if left untreated and that bearing still operating, will eventually create a catastrophic failure. Here we're seeing particulate contamination where we've got debris that gets into the bearing. Debris could be something as innocent as wood or textile threads. Bearings, if we think about internal clearance inside bearings, you're talking about oftentimes less than 1/1000th of an inch. So if you have a textile thread, even a small diameter thread is somewhere in that range, 1/1000th of an inch, and that can create a high point when that ball or roller passes over that thread. It's going to be treated like it's a piece of contamination, and over time that will wear on the steel and create a small dimple or mark here. This is from particulate contamination. Eventually, these little microscopic dents are going to create big giant holes. Here's a large spall that's beginning to form on that bearing. So little tiny debris will eventually cause much larger damage to a bearing. So this usually is going to be caused by outside material working its way into a bearing. And that's usually because a seal on the bearing failed. It was damaged during installation. It's worn out because I said in the previous slide, seals fail 10 times faster than the bearing does. And that can cause premature failure, or even the way that the cleanliness of the lubrication is kept when it's installed inside the bearing. That if it's not perfectly pristine, that will cause bearing failure just from the lubricant itself. So a lot of different ways that particulate contamination can occur. Usually it's seal related, and it's really important that when you repair that bearing the next time that you replace the seals as well as the bearing. Axial Brunels. So axial Brunels, are shown here. They're kind of a triangular shape here, and this is where the ball actually takes and removes material off the raceway itself. So this is some of the ways that this occurs is overloading of a non-rotating bearing in an axial direction. So if I push hard enough, like I'm showing here, where the shaft is pushing from the left against that and pushing this ball up against this outer ring, in some cases, particularly on an angular contact bearing, this is a deep groove ball bearing that I'm seeing here, but an angular contact bearing has part of this outside shoulder removed. That ball can actually pass right over the edge of this and create a Brunel. And so a lot of times this happens during the installation process. If a bearing is being pushed on a shaft and it's not being pressed on the shaft through the inner race, instead somebody's installing it by pushing against the outer race, that will create enough force to actually dent that raceway on the outer shoulder here. And so using proper tooling, pushing on the proper ring, also avoiding any impacts. So not using a hammer and punch to try to put your bearing on. Those are all good ways to prevent Brunels from happening from installation. Radial Burnells are oftentimes due to overload, and radial Burnells will relate to, and this is kind of shows you one here, little oval marks where the ball under load is going to be pressed up against that and actually dents the raceway. And this can be caused from a variety of different things. Here they're showing it where there's really no internal clearance between the ball and the raceways. And so a too tight of a fit, too tight of an installation can cause this from happening, or impact loads can also cause Burnelling or these dents to occur. False Burnells. False Burnells are an interesting type of bearing damage. False Burnells occur when the bearing is not rotating, it's stationary, and it's exposed to vibration. So I had a customer one time where they had a machine that was sat idle for several years, and the bearings were in it, and the bearing machine was in a stamping plant. So they were doing a lot of heavy-duty stamping. They were making fenders and hoods for cars. At some point in, a couple years down the road, they decided to use this machine again. And they turned it on, and they experienced a bearing failure really quickly. And what actually happened was, while that bearing was sitting there installed, the ball will rub back and forth due to vibration against the inner ring or the outer ring or both, and create damage to the raceways at ball spacing or roller spacing. And it's called false Burnelling. And so it's not done from improper installation. It's not done from anything while the bearing is rotating. It's strictly during while the bearing is stationary and under some kind of load and vibration, and it creates little damage right at roller spacing or ball spacing. And when you then fire up the equipment and you start running it, false Burnelling will lead to severe spalling in a very short period of time, because you've damaged that raceway, and you'll get repeated damage, and it exacerbates really quickly. So false Burnelling can be avoided by making sure that your bearings are stored properly, that they're shipped properly. I had false Burnelling occurred because a big, large bearing was transported via train across the country and wasn't stored properly in a box, and we got false Burnelling during the shipping process. So really important, if you have idle equipment, to periodically jog that equipment or run it, just to make sure the grease and lubrication gets circulated throughout the bearing, so that you don't have those rollers continually making or creating damage in a single spot. Corrosion. Here we got an example. This is an inner race out of a spherical roller bearing. You can see that because it's got two rows of rollers here with a center rib, and they're kind of curved or spherical in nature. And right here at roller spacing, you see damage or corrosion. So usually when you see black staining on a bearing, it's indicative of water getting into the bearing and creating that black stain. And the condensation or water will lay there underneath the roller and oxidize that surface. It'll create kind of a dark appearance or black appearance. And then if I were to run this particular bearing, I will get severe damage occurring right at roller spacing. And that's what we're seeing here. We're seeing after this was run, you get this. This is an example of spalling and what spalling looks like, the bearing chuck holes, as I call them. Electrical damage, something called arc pitting. So arc pitting can happen from a lot of reasons, but one of the common reasons is if you got an idle piece of equipment like an electric motor, and someone is using a welder and they have to ground on some metal surface. Well, if they ground on the electric motor, it will put current right through any bearings that are in that motor and create an electrical discharge between the outer race and the ball, or the inner race and the ball, and you'll get a little burn spot right here at ball spacing. And so It can happen because the system is not properly grounded, but it does happen quite a bit from welding. And then when that bearing then that motor or the equipment fires up again, because of the damage to the raceway, you will get severe failures that happen very quickly, right at ball spacing or roller spacing, right where the electrical discharge mark was made on the raceway. Now, electric arc pitting happens when the bearing is stationary. What happens if electric current flows through the bearing while it's operating? Well, then you get something called fluting. And this is one of the more common bearing failures that we're starting to see, because more and more electric motors in manufacturing plants are driven and controlled by something called a VFD, or variable frequency drive. Well, variable frequency drives kind of operate like a rheostat in your dining room. If you've got a dimmer switch, if you will, where you want to turn down the lights or turn up the lights, that's basically what a VFD does, only it changes the speed of the motor. The bad thing about VFDs is they create what's called stray currents, and they get stray electrical discharge that happens out of these little controlling units, and that can pass through an electric motor, and the path of least resistance is oftentimes right through the bearing. And so while the bearing is turning, if you have electric current that flows through the bearing, you get a nice little pattern here of damage, kind of like a washboard surface, or like a sine wave that just keeps going back and forth all the way around the entire bearing on both the inner and the outer race. And this is called fluting. It's pretty easy to spot. Sometimes on one of the two races, it will actually create divots or measurable damage deep into the bearing surface. On the other side, you might just be a discoloration, but you can still see the fluting, you can still see the marks. And the way you fix this is to either use a grounding brush, a grounding ring, which are available for electric motors, or the best solution is using the bearing with ceramic balls. Another good solution is bigger bearings, ceramic coating on the outside race. So this is, again, a very common, more frequently common bearing failure that we're starting to see more and more because of the use of VFDs. And more customers are aware of it and are taking steps to prevent this from happening by either buying a grounding ring or putting bearings in that have ceramic balls or ceramic coated. Excessive axial load when a bearing is operating, especially you can see it here, there is so much axial load. Again, axial load is thrust load, or load that comes parallel to the shaft. So it's going to push one of the races off to one side, which will cause a ball to roll up on its shoulder. So the race path here, which should be right down the center of the groove, instead will be off to one side. And in this particular case, it was hot enough where it actually cold formed the metal and actually pushed the metal all the way up onto the shoulder of the race path. And so that's done because the heat gets so great that the material will actually start flowing. And oftentimes this is because of the stack up of where the bearing goes in. The inner and the outer races aren't perfectly in line, and one of them shifted off to one side in relation to the other. And that can cause the ball to not roll down the center of the raceway. And it's pretty easy to see, and a lot of times it's due to maybe a spacer is the wrong length, or something's missing, and it causes that bearing not to be even where the balls are going to be rolling down the center of the path on both races. Handling damage. So here we've got a bearing race that has chip marks. That's probably more common, where you're going to see an impact load during the installation process. Somebody used a hammer and a punch to try to put a bearing on. And so this kind of damage is directly related to maybe inexperience of a maintenance person who really doesn't know the right way to install a bearing, or doesn't use heat to install a bearing. and tries to use force. And when you see impact damage like this, you'll often see Burnells in a bearing as well, because the balls will dent the raceways because of that blunt force that the bearing's going to see from a hammer or a wrong tool. Cracks. Here we have, again, this is a spherical roller bearing in a race. You can see how the little bit of a curvature here, that's where this bearing is going to be self-aligning, but you see this little split here at a slight diagonal going all the way through there. That's a pretty common indication that this bearing in a race was stretched so much when it was put over the top of a shaft that maybe was just a smidgen too big. And when the shaft is too large to fit inside the bore of the bearing and doesn't have the right tolerance or right fit, that bearing in a race, it's typically through hardened steel, it will crack. And seeing this kind of a split on a straight line like that typically is indicator of a too tight of a press fit. And so fitting practice is something that is really critical. The machinists who are, if the shaft is damaged and they have to remachine the shaft before they put the bearing on there, they need to be educated as to what tolerance range that shaft should be machined to mirror up to a bearing, and it is very application dependent. And so, but it's a failure that you commonly see because the shaft is the wrong diameter. Surface initiated spalling. So this is advanced damage to a bearing. We got a couple different, this is spalling that's happening kind of at ball spacing here. And here is spalling that's occurring all the way around the bearing. But you'll notice this is, again, one of those double row spherical roller bearing in a races. All of the spalling damage is occurring on one side. So this surface is really pristine looking. This is really heavily damaged. That tells me that this set of rollers was under load while this one was not. So there were probably some axial loading issues. And this particular bearing is unique because it comes with a tapered bore in some cases. This could be a situation where the bearing was installed with too tight of the taper was too much into the bearing and got relieved of all of the internal clearance on one half or one set of rollers, and that would cause this severe spalling damage that would happen. This one could be starting out as impact loading, where you've got a small Burnell, and then over time, through millions of revolutions of those balls going throughout the bearing, you'll actually get damage, severe damage right at spacing where the original Burnells occurred. Misalignment. It's kind of hard to tell, but if you look at the damage to this bearing, we got damage at this part of the race down here at the bottom, and then we've got severe damage here on the top. So really the ball is kind of running at a diagonal path throughout this bearing, and that will cause spalling on opposite sides of the raceway. And so this is an indicator that this bearing is misinstalled on the shaft. A lot of times bearings will go up against the shoulder on the shaft and need to be seated all the way against that shoulder. Actually, two different diameters, one with the bearings on and a bigger diameter where the side face of the bearing can actually go up and butt up against to locate the bearing. Well, if you don't put the bearing all the way up against that shoulder, that can cause misalignment. Or if the shaft itself is damaged or bent, that also can cause misalignment. So, but the spalling is going to be reflective of the overloading condition on both sides of that bearing, because when the bearing is misaligned, the raceways are not, or the outer race and the inner race are at an actual angle to each other instead of being exactly parallel, is when you start seeing misalignment damage. And so very important that you look at the equipment overall to see that the housing and the shaft are properly aligned, that the bearing, the shaft is not bent, causing the bearings to be misaligned. Overheat and meltdown. This kind of looks very similar to the very first picture that we saw, where the bearing saw so much heat that it's actually starting to melt. As you see colors appearing on bearings, that's a good indicator as to how much heat it saw. So an amber color, for instance, is in the 400, 450 range. When you start seeing blues, blues up around 550, getting to 600, or purples. So this is an indicator that if I took this bearing apart and I saw all these bands of color, I know that bearing saw heat that is much greater than what I'm going to typically want to see in an application. As I may have mentioned before, holding your hand on a piece of equipment would be one way that old-time maintenance people kind of determined whether a bearing was operating at the right temperature. If you couldn't hold your hand on it, then oftentimes you knew it was running too hot. In this particular case, and that's like 120 degrees, this is seeing 500 degrees or 600 degrees. And so we know we've got some problems. And when a bearing is running at that kind of temperature, you'll get flowing of the metal. And ultimately, this bearing will end up looking like that because the grease itself, most greases don't have the ability to go and run at that kind of a temperature. The grease will melt, it'll run out of the bearing, and then you've got metal-to-metal contact, and it doesn't take very long for that bearing to start seizing up and looking like this. So we've explored a lot of different types of bearing failures, and the thing that you should take away from here is that bearings are designed for a long life, and the most I ever came across was a bearing that lasted 47 years in an application where they were running 16 hours a day. So bearings, if they're properly maintained and properly installed, can last a long time. Most bearing applications are designed so that the bearing can last at least 30,000 hours, which is 3.5 years of continuous use. But despite that, that's theoretical life. The real life is that bearings sometimes are installed by people who don't know what they're doing, that they don't know how to properly lubricate them, that there's other damage on the equipment that can contribute to bearing failures, that there's vibration. There's a myriad of different things that can happen that would cause bearings to fail prematurely. And a lot of times that's used or due to things like lubrication, which is almost half the bearing failures occur from lubrication. A third of them occur because of misinstallation or people who aren't quite sure of how to put a bearing on. About 20% of them are because the seals fail. So just those three things are typically all preventable. And so by doing a good job of having proper maintenance practices and people who are properly trained, we can really cut down on the amount of bearing failures that customers going to see, and making sure we handle the bearings properly, and we have a good preventative maintenance program so that they get relubricated on a regular basis. Those are the best ways to really avoid bearing failures. I appreciate your time. Hopefully you have a better understanding about how bearing failures occur and how bearing failures could be prevented going forward. If you're interested in learning more about bearings in general, the Bearing Specialists Association offers a program called the Certified Bearing Specialist Program. And by going through a accelerated curriculum that touches on a lot of different topics related to bearings, you can earn a certification as a certified bearing specialist. And whether you're a bearing distributor or manufacturer or end user, I encourage you to take a look at that if that's something that you're looking to kind of expand your knowledge of bearings in general. I appreciate your time today. Again, I'm John Masick from Bearing Service, and I hope you have a great day.